We are in an unprecedented era of largest number of refugees. Every 2 seconds, one person is forcefully removed from his or her house. Discrimination because of religion, race, and politics resulted in the displacement of the refugees.
Said objectives of this project is to propose an accommodation for unaccompanied children using minimum UN requirements and Jordanian Green Building Code, to innovate by designing a smart skin that responds to the climate, to educate refugee children and create awareness about them, and to optimize energy through building orientation, PV panels, and use of smart skin.
In this video, we will have 5 stops: introduction, site analysis, concept and design, IES analysis, and conclusion. And we will start with introduction.
25.9 million refugees. More than half of them come from 3 countries: South Sudan, Afghanistan, and Syria. Let's focus on Syria. 6.7 million refugees come from Syria. 10% have been displaced to Jordan, a country that shares borders with Syria. In Jordan, there are 3 refugee camps: Al-Zatari, EJ, and Al-Azraq camp. We will focus on Al-Azraq camp. Let's move on to our site analysis. Al-Azraq camp is located in Al-Zarqa Governorate of Jordan. It is 100 kilometers away from Amman, the capital of Jordan. The main entrance is from the north, and Al-Azraq camp has 7 villages. We will be focusing on village 3. The site is strategically located less than 100 kilometers away from more than one service building. Notice the wind from northeast and southwest. From site analysis, we move on to our concept and design.
With that formula in mind, we obtained our form and we duplicated it to create a social space for the children. We refined that form to get UN compliant final design. And this is our final design.
We refined the final design using the Jordanian Green Building Code to get to the base case design, by elevating one mass up for ventilation, by changing materials, by adding a green roof, and by having no more than 40% glazing. For base case materials, we took into consideration the maximum U values advised by the Jordanian Green Building Code, with 0.8 maximum for roof, 1.6 maximum for wall, and 3.3 maximum for windows.
We used results of the total energy of base case for each north rotation to achieve optimum orientation. The result was rotating north at 90 degrees.
We got inspiration from the Islamic mafruka native to the Sham area for the pattern of our kinetic skins.
We designed a facade skin with X and Y louvers. When X louvers respond to thermal changes and Y louvers respond to daylight changes. We will use linear slider mechanism to achieve the motion required. Notice how the skin bends due to the force acting on it, and rather than it rotating, it is limited to motion work within the track.
In summer, the skylight will fully close during daytime to reduce solar gain. In autumn, one wing will close depending on thermal conditions, and in winter it will fully be open to increase solar gain. We will use rotation mechanism along a central shaft in different degrees to achieve the motion needed.
We ran solar shading analysis of base case and realized how much solar gain was on the roof. To reduce that solar gain, we added PV panels on the top mast and green roof on the bottom mast. IES takes green roof as insulation layer and does not account for evaporative cooling. The application of the green roof reduced yearly solar gain by 29%.
A generated PV array layout by IBC Solar on the same roof area tells us that we can produce up to 36.5 kilowatt peak, more than we expected by our IES analysis. We use daily running mean temperature analysis of base case to obtain our design days. For summer scenario, we use 26th of July. For winter scenario, we use 10th of February. And for autumn, we use 15th of November because its climate is not fully within the comfort zone. We obtained the azimuth and altitude of these days to see how the sun is affecting our building. For 26th of July thermal simulation, temperature was reduced by 21% at 9 a.m., 23% at 12 p.m., and 25% at 4 p.m. Comparing the southern facade of the base case to the improved case, there are more cooler hues due to the shading of the kinetic skin. As for solar gain, it was reduced by 60% at 9 a.m., 68% at 12 p.m., and 60% at 4 p.m. We will be focusing on the 12 p.m. scenario. For 12 p.m. summer scenario, west facade louvers will be fully open, south facade X louvers will be fully closed, and the Y louvers will be fully open. The courtyard will not be glazed, and the skylights will be fully closed to the sky to block solar gain. Moving on to the daylight analysis, on the left side, there's the base case with a daylight factor of 34, and on the right side, there's the improved case with daylight factor of 22. It's required by the Jordanian Green Building Code to have 80% of the space daylit, thus the black spots are acceptable. Now let's have a look at the interior from the point of view shown. Comparing the red spot in the base case to the blue spot in the improved case, there's a 46% reduction. The lux values in the improved case are better suited for less glare, yet they comply with the minimum of 270 lux by the Jordanian Green Building Code. As noticed in the image on the bottom right, the glare is reduced and the area has lux mostly between 250 to 550, where 300 to 500 lux is recommended for library. Moving on to the CFD analysis relative to the base case on the left, kinetic skin on the improved case on the right reduced the temperature of the highlighted area by 24%.
The higher prevalence of a blue shade in the improved case highlighted area reflects a reduced interior air velocity of 0.22 meter per second and below.
Both analyses comply with Lawson-based criteria of 2.5 meter per second or less for sitting in regards to pedestrian comfort. For our comfort range analysis, we achieved lower predicted mean vote score in the highlighted area of the improved case. The number is closer to the zero compared to the base case. A comparison of the psychometric chart of both cases showed that the improved case is in closer proximity to the ideal range of comfort adapted by ASHRAE.
Looking at the southern facade on February 10th, we noticed less solar gain on the facade due to shading of the kinetic skin. Focusing on the 12 p.m., we managed to stay within the comfort range. As for the solar gain, it increased by 2.3% at 9 a.m., increased by 23.6% at 12 p.m., and decreased by 9.3% at 4 p.m. For the 12 p.m. scenario in the winter, the western and southern facade will be fully open and half of the courtyard will be glazed, while the skylight skin will be fully open to maximize solar gain. For daylight analysis, we will focus on the upper bedroom mass of both cases. On the left is the base case, and on the right is the improved case. Using the numeric grid and looking at the same spot, the base case daylight factor is 19, where risk of glare is high. However, the improved case has an adequate daylight factor of 5.1 that does not require artificial lighting during the day. Let's have an internal look from the point of view shown. Comparing the same spot, there is a 48% reduction in the improved case relative to the base case. Looking at the two images below, base case lux ranges between 750 and 950 with glare risk, whereas the improved case bedroom lux ranges between 250 and 350, with 300 being the ideal lux for bedroom spaces. Moving into the CFD analysis, the same color indication reflects different numerical values relative to the scale of each case. Both cases fall within the comfort range of interior thermal conditions. For the PMV comfort range analysis, we achieved interior conditions of -0.044 in the bedroom area of the improved case, which is closer to the ideal 0 of PMV scale compared to 0.25 in the base case. Looking at the psychometric chart, the 2 points on both charts correspond to each other.
For autumn scenario, temperature was reduced by 9% at 9 a.m., 13% at 12 p.m., and 14% at 4 p.m. As for solar gain, it was increased by 5.2% at 9 a.m., reduced by 11% at 12 p.m., and reduced by 25% at 4 p.m. We will focus on the 12 p.m. scenario.
For the 12 p.m. scenario in autumn, the western facade will be fully open, the southern facade X louvers will be fully closed, while the Y louvers will be half open, and half of the courtyard will be glazed, while the skylight skin will have one wing open to stabilize thermal gain. Moving on to the daylight analysis, on the left we have the base case library with daylight factor of 40, and on the right we have the improved case library with daylight factor of 26. A closer look at the numeric grid in the area below the skylight shows a daylight factor of 18 in the base case with higher risk of glare, and a daylight factor of 10 in the improved case. Note here the skylight skin is partially open to help reach thermal comfort through solar gain. Let's have an interior look. Base case has higher lux, beyond recommended of 300 to 500 for libraries. As noticed in the image on the bottom right, the glare is reduced and the area has lux mostly between 250 to 550. Looking at CFD analysis, the improved case library temperature is 15% less than that of the base case, and it falls more squarely within the comfortable thermal range. As for the predicted mean vote analysis, comparing both cases, we had a value closer to the neutral zero of predicted mean vote in the improved case. As for the psychometric chart, the base case falls closer to the comfort range, and we think that is because the analysis takes the average of the full day, with noon time of the base case being hot compared to the improved case.